Hello my dear students, I am B S Pandey, your physics lecturer. Today in this series of Standard 12 video lecture, we are in lecture number 84. Alright? Lecture 84, and hopefully this is the last lecture of this particular chapter. Actually, today we are going to deal with the topic. It is mentioned in several books in electromagnetic induction, that is the AC generator. But here we are going to study in this alternating current AC chapter. It is very related with this chapter. Alright, chapter number 7 of NCERT. Today it will be finished, and AC, alternating current. After that, we will solve assignment of this chapter, my dear students. So today's topic of our lecture, it is AC generator. AC generator. My dear student, actually the DC current, DC current, it was very expensive, and to drop down the cost of that very much expensive DC current, AC current or the AC generator was considered as a very great research. It was done by the Nikola Tesla. Alright. So we are going to study this particular topic. What this AC generator actually do for us? So we will give as an input in this AC generator as our mechanical energy. You might have seen in the party function, alright, or the marriage function, a generator, a machine, it is kept, alright, and a person used to hand that generator giving a mechanical work, and it start. It might be, you have noticed, auto having the same mechanism. Auto driver used to wind up a thread, a rope below the auto engine, and it wind and pull quickly, so it starts. Alright, or the very small generator, that is the Honda generator, it also works on the same mechanism. What do we do actually? So we give the input as a mechanical energy and takes output as a electrical energy. So it converts mechanical energy, into electrical energy. Okay, my dear students, it converts this mechanical energy into electrical energy for us. Alright. Now, on which principle actually this works? Remember, as I have told you, because this DC was very expensive, that's why the AC generator was considered the great research. We know that, na? If this is the AC, let me discuss few things. If this will be the AC graph that we will discuss right now, in which this is the peak current. Suppose this is the peak value. This is the AC. And we know that we have discussed in electromagnetic induction chapter, it will not receive continuously. But in DC, it receives continuously. This peak value, suppose it is I naught, in DC circuit, it receives continuously. But here in AC circuit, we got this peak value for very small time interval. Alright, for T by 4, we got the maximum value. Now, at T by 4, not for T by 4. Now, we know that heat is I square RT. If we want to transmit DC current over the large distance, what will happen? This current continuously moving through the wire, having the great resistance because of the great length for the large transmission. So in the same time, it generates the heat which is more in compared to the AC. AC, you know that the peak value will be smaller. Why? Because it giving the high current, that is, suppose it is the 10 ampere or the 5 ampere, suppose it is the 5 ampere, this is also the 5 ampere. So the peak value, this 5 ampere, it is given continuously, generates the maximum heat, but it's 5 ampere, it is coming for instantly. So it will generate the less current, less heat. So it would be the very expensive. Why? Because the maximum heat generates throughout the wire, it will be not useful, it will be the lost. Okay, so this AC was considered. That we have discussed in very detail, alright, while studying RMS value and peak value of AC current and voltage. Alright, you are not new for this. Okay, now the principle over which this AC generator works. Remember, you have to study this particular topic, the DC generator, as well in your standard 10th, but teacher used to give the concepts of AC generator as well. Alright, so this is the principle, and it is based on the principle of electromagnetic induction. Electromagnetic induction. Alright, EMI. That was our chapter number 6, electromagnetic induction. This will work as the principle. Over this principle, our generator is based. That is the AC generator. Remember, alright. Now we will try to understand its construction and working. You know, my students, I will provide you a clip that will explain you the mechanism of this AC generator, how it works actually, how it looks like, how the coiling are there, how should be the magnetic field over there, alright, all the things, and what are the components in this particular generator, all the things you will get very clearly from that video clip. Here we will basically do the calculation. Alright, so the construction and working. And working of this AC generator. So let me construct the AC generator over here. This is magnet, but we use here concave or convex phased magnet. Remember, it is curved. Alright, suppose if you are having a long magnet, you cut out the magnet cylindrically out from there, so it looks like. This is our armature coil that will rotate. I'm trying to make here the 3D picture so that you will be able to understand all the things clearly. This is the north pole and this is the south pole. What will happen? This pole will provide the magnetic field from north to south, in which this coil is kept. This is the axis of rotation. This will be the axis of rotation. This will be the axis of rotation. About this axis, it rotates. Now, my dear friends, look at it. One end of this coil, this is the armature coil, A, B, C, D. The one end of the armature coil, it is connected with a ring. Alright, it is called a slip ring. So, it is connected with a ring. Let me draw here the ring. Okay. It is connected with this one end, it is very clear, connected with this ring. As this coil will rotate, this ring will rotate. Alright. And the second end, without touching the ring, it goes inside the ring and move out. Move out. Look at here. Okay. This particular end not touching the ring. And it is also connected with another ring. In this way. This is also slip ring and it is connected over here. I hope you are very clear. Now, as this total armature coil will rotate, remember both the ring will rotate and both the section will rotate, but this end which is coming from D, it is not touching any one of the ring. Alright. Now, to get the output, we use here carbon brushes. This is the carbon brush, and this is also the carbon brush. Alright, there must be some friction with the ring and the carbon brush. That's why a spring is provided, so that this carbon brush, as per its convenience, can move forward and backward. Here a soft spring are provided. Now this spring are connected with the conductor to get the output. Here we can get the load, we can apply the load. Alright, so this is the rings S1 S2. Basically I'm not going to write, you have to write by yourself. Listen carefully. S1 S2 are the two slip rings. This B1 and B2 are the two carbon brushes. Alright, and this is the soft spring. Remember, here we will get the output. Here we will get the output. Now try to understand its working, my dear students. As we will provide here the input as a mechanical work, it means we have to rotate this coil. Suppose we have rotated this coil, we have given a force, look at here carefully, we have given a force at this arm in upward direction F, and at this arm the force in downward direction. Alright, due to this couple, that is the couple of the force, what will happen? This coil will rotate. Alright, if this is the coil, due to the force it is acting from here up and down, it will twist, it will start rotating. Now it is very important to find the direction of current. So in note point you should write the direction of current, direction of induced current obtained by Fleming's right hand rule. Remember, right hand rule that I will apply right now to find out the direction. Look at it carefully, my dear students. This is the coil. Let me find a copy. Yes, look at here. This is the copy. So the coil A, B, C and D. If we apply a force in upward direction, look at here, in upward direction, and this is the coiling, this is the wire, alright, of might be the n number of turns, this is the wire. If this is the direction of force, what is the magnetic field? Direction of magnetic field from north to south, and this is the magnet north and south. It looks like the cylinder. Why it is being cylindrical, the concave? Because remember students, if the magnets are of this shape and it starts, if this coil starts, so you can see here the distance, and when it comes here the distance is different. It might be the magnetic field will be different and it start damping. Alright, it start damping. That's why we use to concave, so that as it will rotate at every point, the same distance and same uniform magnetic field will be given to the coil. Now my dear students, here this is the direction of force. Alright, this is the direction of magnetic field. So Fleming right hand rule, try to recall, this is the Fleming right hand rule. Index finger represents the direction of magnetic field. This represents the direction of motion, that is the direction of force, and this will represent the direction of induced current. Alright, that is the output current. Now this is the magnetic field and this is the force, so you can see the direction of current, it is in upward direction. Alright, or you can find out by the right hand rule, Maxwell right hand rule also. V cross B will give you the direction of current. V cross B. Put the forefinger along the V direction of velocity and move towards the magnetic field, that is V. So the V will be in upward direction, velocity will be in upward direction. So you can see, look at again here, this is the V and the magnetic field in this direction. So V cross B. So the current will be in upward direction. Alright. Yes. So dear students, here we are getting the direction of current, the magnetic field in this direction, the force in upward direction, so the current in upward from A to B. This is the current from A to B. Of course here it will be from C to D. This is the current. Now if this is the direction of current, my dear students, you can see if the current is coming from here, it means this is the positive end and this is the negative end, because the current is coming here. Alright, this is the positive end and this is the negative end. But it is very important, my dear students. Here, if it is moving this way, after the half turn, what will happen? After the half turn, try to understand very carefully, try to understand. After the half turn, what will happen? This CD will be in this direction. CD will be in this direction at the place of AB. And now over the CD, the force will be in upward direction. But CD is connected with the same brush. That's why now this CD is in this side and this will experience positive. It means after half cycle, this will be positive and this will be negative. It means after each half cycle, the polarity is being changed. And it is changing. Due to this change in polarity after each half cycle, the current generated, the induced current, actually this is called alternating current, because alternatively it is changes. How it will change, what should be the value and how this value should be increased or decreased, we will study over the graph. But this is the working of, my dear students, AC generator. I hope you understand. Now, try to see this video clip so that you can understand very well the mechanism of AC generator. Alright, so look at the video clip.
Is an electric generator that converts mechanical energy to electrical energy in the form of an alternating EMF or alternating current. Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip rings and a load, which may be a galvanometer as shown. Working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Direction of induced current. Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes a half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So, the current will flow from B1 to B2 through the galvanometer. Now during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule, current will flow in the direction ABCD, that is, from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation. Graphical representation of induced EMF. Suppose the armature takes t seconds to complete one rotation clockwise. At time t is equal to 0 second, the armature ABCD is vertical with arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily zero. Hence, the induced EMF at this position is zero. During the first quarter rotation, the induced EMF increases. Then, at time t upon 4 seconds, the armature becomes horizontal. At this position, the rate of change of magnetic flux momentarily attains the maximum value. Therefore, the induced EMF at this position is maximum. During the second quarter rotation, the induced EMF decreases. Then, at time t upon 2, the armature again becomes vertical and therefore the induced EMF is zero. During the third quarter rotation, the induced EMF increases but has an opposite polarity as compared to that of the first half rotation. At time 3t upon 4 seconds, the induced EMF attains its maximum negative value. During the fourth quarter rotation, the induced EMF decreases and becomes zero momentarily at time t seconds, as the armature is vertical once again. So the magnitude of the induced EMF is sinusoidal.
I hope, my dear students, you enjoy that video clip as well. You have understand the mechanism of AC generator. You are able to write in examination now. Alright. Suppose, my dear students, if this coil is rotating with angular velocity omega. Now we are going to plot here the graph. Okay, and we are going to study how much EMF or the current induced. This coil that we have drawn here, suppose this coil have a resistance R. Alright, how much? Resistance R. Number of turning, how much? It is M, that you have to study. The magnetic field it provides, it is B. Alright, the area of this coil that it can trap the flux, that is the area, suppose it is A. Alright. These are the quantities you should remember. These are the quantities which you should remember. Now, my dear students, we are going to do the calculation and plot the graph. Look at here. Okay, so suppose this is the coil, this was the magnetic field in which coil is kept. This one is rotating. I hope you will recall that we have studied in EMI. This is the magnetic field and area will be also in this direction. This is the magnetic field and this is the area vector. Alright, how many turns do we have? Yes, N. And it is rotating about this axis with which velocity? Omega. Alright, suppose if this coil rotated like this way, for certain angle. This was the magnetic field, direction of magnetic field B. It is rotated by angle theta, which is in time t omega t. Alright, Now this is the area vector. So what we can write the flux, my dear students? We can write the flux as n times B dot dA, that is BA cos theta, which is omega t. Am I right? Yes. Why we use here the n times? Because for the one turn the flux will be if 10, so the 2 turn will acquire total the flux, it is 20. So n turns will acquire the total flux, n times the flux by one turn. Here, if we are having the flux, then using Faraday's law, according to Faraday's law of EMI, my dear students, what we can write the induced EMF? I induce, E induced, we can write minus d phi by dt. Am I right? D phi by dt. Alright, already we have taken here the flux n times, so we will not provide again the n, which is NBA, altogether a constant, NBA, it is constant. We have to differentiate this cos omega t over dt. Remember, it is rotating with the constant angular velocity omega, so the omega is also constant. What is the definition of cos? So the definition of cos will be the minus sign, and minus will be plus. So NBA, it is the sine omega t into omega, which is the constant. You know, with the differentiation what we do? NBA omega sine omega t. What is this? This is the E induced. Okay. Now try to understand here. For what value this E induced will be, for what condition this E induced will be maximum. So this E induced will be maximum when sine omega t will be maximum. And sine omega t, it will be maximum for which angle, my dear students? So try to see here the graph. Let me rub this one. Kindly note down. Try to make here the graph. Alright, voltage and omega, that is the time, you can say, or the theta, whatever may be. Here we will take the omega t, alright, and the theta, or you can write for time period t, and this is the E induced, that is the current, voltage. So you can see here the E induced, it is changing because this all value is constant, and this constant value, that is the maximum value, this will be NBA omega, but it is changing with the sign. That's why this is called a sinusoidal function, and it will start at t equals to 0. What will happen? If we will put the value of t as 0, you will get the 0 and the sign 0, 0. But it starts giving a graph like this way. Am I right, my dear students? And this is the maximum value. If this maximum value that we have studied in EMI, it is denoted by E naught. This is minus E naught. So we can write this E naught as how much? NBA omega. NBA omega. This is not very difficult to understand, my dear friends. Okay. Now we'll try to find out the time. Okay. We'll try to find here the time in which it reached to its maximum value, and what should be the orientation of the coil, and in which time it reached to the minimum value, and what should be the orientation of the coil. Alright. So look at here carefully. Okay. This one is the case. This one is another case. This will be the other case, and this will be the negative value, and this will be again 0. one by one we will discuss all these cases. Okay, my dear students? Yes. So let me draw this case first. Here, in this case, the induced EMF that we are representing here, it is 0. What we will write the current, student? So we'll write the current here. We know that according to Ohm's law, it is E equals to IR. E is equals to IR. So it will be I is equals to E by R. That is I naught sine omega t. There is no change in phase. The maximum value we will get of voltage, at the same time we will get the maximum value of the current. But here we are having the concept of flux something different. The flux, if the flux changing maximum, then we will have the current maximum. Remember, okay? Here, to reach from this point to this point, that is the maximum, from this point to this point up to the maximum, here the flux taps 0 and changes by the maximum flux, alright, for the maximum flux at this time. So we can write here the time is the total time between the field if our coil is in this, suppose this is the coil, alright, this one, look at here, this is the magnetic field. Try to understand this guy, magnetic field, and this is perpendicular, that is the flux is maximum. Why? We have written the equation as sine here. After differentiating, it means the flux will be of the cosine value, and cosine value will be, the cos will be the maximum if theta is how much? It is 0. So this is the flux trap, and this is at time t equals to 0. Alright, this is the time t equals to 0. Alright, now for this case you can draw this coil wheel, looks like this one. This is the magnetic field and the flux will be 0. Okay, it is rotated by 90 degree from here to here only. It is in this way, it is rotated by 90 degree, and the time it will be, we will write here the time. Here the theta is 0, here the theta is pi by 2, this angle is pi by 2, this is the angle is 0, this is the maximum, its area in this direction, its area in this direction. It is making with the magnetic field 0 degree, it is making with the magnetic field as 90 degree. Now for the third case, for this one, if we will plot the diagram, this was in this direction, in this orientation, it moves 90 degree. Now again it will looks like this one, or the area it will goes its area now in this direction. Okay, I hope you understand. Again this theta, it is 3 pi by 2. Now it is from here maximum value, and again this theta, it is, sorry, the time we will write here. We have not written the time here, also we have not written the time here. Theta, it is 270 degree, 3 pi by 2. Alright, now after this orientation, the last orientation will be like the initial one, rotated from here, again this one, and again it will rotate like this way. Alright, so the magnetic field area vector will be in again, or you can consider in downward direction, area vector. It is making again 90 degrees, so that the flux is 0. Alright, so here the flux 0, here the flux 0, here the flux maximum, and it is maximum theta, it is 2 pi. Alright, it was 0 to, this was 0, this was pi by 2, here pi, sorry, the third one, it is the pi, theta was here, the third case, 1, after this rotated, the maximum value, it is the pi, you can see the maximum, and it is 3 pi by 2. Alright, there was a slight mistake. Now the time, this is the half cycle 0 t by 2, and this is the half cycle t by 2 to t. The half of the half, that is the quarter cycle, t by 4, and this is the t by 4. Alright, so we can write here the time as 0, it is t by, this one t by 4, this one t by 2, and this value, it is again t by 2 plus t by 4, so it will be we have not mentioned here for this value. In between this value we are represented. So this is the actually the working of the AC generator, and this is the graph of AC generator. Okay, my dear students, we got one equation that we have studied already in electromagnetic induction. It is Et as E naught sine omega t. This is the voltage generated by the generator, and I equals to I naught sine omega t. And what is the value of I naught and E naught? Already we have written. It is the NBA omega, it is E naught, and NBA omega divided by R, it is I naught. Alright, my dear students. So this is all about the today's lecture, my dear students. Thank you very much.